Hello everyone, welcome to another problem session. So this is our first session in which we're going to use relativity, special relativity, to solve problems in electricity and magnetism. So there are some example problems here that you may think of. One is a very simple one. A point charge is moving. So here is a charge. It just coasting at some speed v, and of course dv dt is 0, no acceleration. And we want to find the electric and magnetic field of this charge. It looks like a simple problem, but if you try to do it just directly from what you have learned from electricity and magnetism, it's going to be really nasty. Okay, but if you do it, think relativity, it can be very simple. Okay, and we'll do this. Second one is like a very similar. That if a current is carrying current I, you have a magnetic field. You know this. You have a magnetic field circulating this way. But I is as if the charges were, if you look inside there, the charge Q is distributed through it. And so we can say how much charge per unit meter in terms of this. And you can assign a drift velocity V. So it's kind of like that, but it's a whole bunch of charges here in infinite wire. And so the way you do that, you can see this magnetic field that's here. If I jump into this frame, then now the charges are there, but their V is 0. See, it's this frame, it's like that, but in this frame attached to the wire, which but attached to this electron, say attached to that electron, it was this electron that was moving. So it's moving with the electron, and we can assume that everybody is moving the same speed. So it's really nobody is moving. So if you look at this electron, nothing is moving. So nobody moving. So here you only see electric field. Over here you can see magnetic field. So it's like we should be able to figure out the relationship between this situation and that situation, and that's also relativity. Another great one is this one. You know that if you have two parallel plates, you have an electric field here. But if the parallel plates are moving, you have a frame in which these guys are moving, both of them constant velocity. So it's almost like that. Over here, with moving velocity, then I can think of this plate, top plate, as a current that way, and bottom plate current that way. And so there should be a magnetic field between this. You probably know that if the current, it will be surface current density. And so there will be a magnetic field here instead of electric field. So you had electric field over here, and you didn't have any magnetic field there if they're not moving in a frame. But in a frame in which both are moving at constant velocity, you're going to find some magnetic field there. You can also find electric field, but you can find some magnetic field. Electric field also becomes very strong in here. So there's both electric field and magnetic field here. So we're going to do all these three problems. Now, we talked about electric field, magnetic field in terms of transformation. This transformation in terms of four vectors. So relating to four vectors, let's just do just a review relating to four vector notation. So so you have some vector I. So there are two types of four vectors, right? You have a contra vector and covector. So this is like a contra, and this is covector, contra, and covectors. So this one stands for the zeroth component, first component, second component, third component, and this one stands for same as that, but minus of this, and minus that. These are negative. That. So for this property, I'm calling V. It could be a property like energy and momentum, and so that will be, you say energy momentum. This would be Pi will be energy over c, and momentum, x momentum, y momentum, z momentum. So these three components, and covector will be energy over c minus px minus py minus pz. And we have a dot product idea. Dot product, a scalar product, is pi and pi. So we'll take a dot product of these two guys. What we mean is we sum over I equals 0 to 3. That gives a dot product. And so dot product is a scalar. Okay, and this scalar is over here is e square over c square minus px square minus py square minus pz square. And because it's a scalar, it's going to be same in every frame. So if you have two frames and this is unprimed and this is primed, so this will be equal to e prime square over c square minus px in the prime frame, py in the prime frame, pz in the prime square. This will of course e square over c square minus p square, and this is e square over c square minus e prime square minus p prime square. So because this is a scalar, it's going to have same in both properties. So scalars are things which have take the same value in all inertial frames. Okay, so why I'm telling you this is if I have one index, I have one vector. So there is you can have two indices. So one index, the transformation is by index. Okay, so if I have in the other frame v prime I, so v prime I, let's see. So this one is in the unprimed frame, and v prime I in the other frame will be is v prime 0, v1, v2, v3. Now these primes, now these will be related to that. If I have like this, then v prime, so let's see, if I have a c equals to 1 unit, then v prime 0 v0 is gamma v prime 0 plus u v prime 1, and v1 equals to gamma v prime 1 plus u v prime 0, and then v2 equals to v prime 2, and v3 equals to v prime 3. So this is the transformation which we call Lorentz transformation, and we looked at it in another notation. So I'm gonna try to tell you that notation. So if I have a vector vi, then we can write this all four of these by writing lambda I and j v prime j, and I summed over j equal to 0 to 3. So this whole thing can be written like that. You can see with lambda nicely organized, this is gonna lambda 0 0 is this guy, lambda 0 0 is v is gamma. You remember gamma? gamma in this case, gamma will be 1 over square root of 1 minus u square over c square, and c equal to 1, just 1 minus c square. And then you have a gamma, and then lambda 0 1 is a gamma u, gamma times u. Lambda 1 0 is just gamma times u. Lambda 1 1 equal to gamma, and lambda 2 2 equals to 1, lambda 3 3 equals to 1, and everything else is 0. So you kind of organize this nicely: gamma, gamma u, 0 0, gamma u, gamma 0 0, 0 0 1 0, 0 0 0 1. So you can think of this as organized in a matrix, right? So you can easily check. The first one is row, so this is go row, and this index go column. Okay, so each index transforms like this. Now we can have properties which have two indices. We call it two tensors. So a property, so two tensors. So it can be something like some property A, which has two indices, both upper indices. So this can be a whole bunch of them. The first one upper, but the second one lower. First one lower, but the second one upper, and both can be lower. So property A can have 4 different representation in terms of 4 vectors. Okay, in the 4 vector notation, this becomes two tensors. So there are four types. In addition, what these guys are, electric field and magnetic field, is actually part of the F4 tensor. So E and B are part of a F2 tensor in 4-dimensional space that we're talking about is space-time. So what do we have? We have an electric field. We have a tensor. We usually use letter F for it, and instead of ij, well, let's ij. So this will be like this is 0. So this tensor will have electric field x component, electric field y component, electric field z component. This will be negative, 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 and then you have ex, ey, ec, and then you have a 0 along the diagonals, and over here is minus bc, over here is minus bx, over here is by, and then is antisymmetric. Bz gets minus sign, this becomes minus by, bx. Okay, let me just check it. Yeah, so what you can see that if I can read this. So this is like a 0 1 component, 0 2 component, 0 3 component. This is 1 0 component, 2 0 3 0, and this is if you go row 0 1 2 3, and if you go column 0 1 2 3. So basically you have a Fij equals to minus Fji. That means diagonals are 0, and this is antisymmetric. So now we have two index. So if in this prime frame, if you have a f prime ij, one of these, how does it become f? So the prime frame versus unprime framed. So what happens is, say if I wanted a b, then it will be take up one of these lambda, and so this I with this I transform that index, and then I equals to 1, 0 to 3, and then another lambda to transform this guy. So another lambda, you can put it on this side or this side, doesn't matter, another lambda, and you have a b j. So if I wanted to say f, say what will happen to 0 to, this should come from I equal to 0 to 3 lambda 0 I and also after also sum over j. So the double sum j equal to 0 to 3. So j equal to 0 to 3 lambda this 2 j f prime I j. So you can see what this component will be. So when you work it out, so this should be, if you look at here, 0 2. So this will be minus ex ey equals to, I work this out, and so this is where this will be obtained, and then similarly all the other formulas will be obtained. So I'm just going to use this formula. You can try to obtain this yourself by doing this out. So this will have the same prime form. So this will look like everything with a prime, exactly same structure, and then lambda is like this. I just read off lambda from there, and if you want to put c back in, you know, this one has a c square down here, and this one, so that's when you put c equals to 1, you just impact that part. Okay, so I will use this. I'll figure out a frame in which its formula is simpler, and then I transform into the frame that the problem is stated. Okay, so that much is my trick. Let's do the problem now with this background. Okay, so you will see the problem is rather easy. So if it's moving at a constant velocity, what I'm going to do is I'm going to just pick a frame where I'm going to put the particle at the origin of this, and I'm going to call this K prime frame, and K frame is just going to be my, and this is going to be x axis, so this x prime axis, x axis, and this is common, I mean it's along the same line. Okay, so this is a common x axis. This the structure will be at some point in time, this O prime and O will be at the same place. That's the one we've been using, and I'm going to assign this the same velocity as this. So this will be at rest in K prime. So it's very easy to know at some point P, what should I, P will have a coordinate x prime, y prime, z prime, t prime, and in terms of this, its coordinate will be x, y, z, and t. Okay, so we already know the transformation between this and this, right? Like t is gamma t prime plus this is v over c square x prime, x equal to gamma x prime plus v t prime and y equals to y prime, z equal to z prime. And the reverse part, so this is one way, and I want to reverse it. You have a t prime equals to gamma t minus b over c square x prime equals to gamma x minus v t, y prime equals to y, and z prime equals to z. So we have this, we can go from one to the other just like that before, right? So in here at this point, using this frame, I'm gonna write with respect to this, what the electric field will be. So electric field, because sitting there at that point, electric field was just pointed away from there. So electric field will just be, electric field will be whatever this q is, q over 4 pi epsilon naught, and this vector, let's call it, this is some vector from here is r prime vector, over r cube. So this is the unit vector. So this is like a u hat r prime direction times r prime square. So that's what this is. So this, and because it is stationary, it doesn't really know, it just knows the coordinate, and then that's it. It's you can write this as, let's this whole thing, call this whole thing q. So q is q over 4 pi epsilon naught, and this just going to be x over r prime cube I hat plus y, this prime, y prime r prime cube j hat plus z prime r prime cube k hat, as before, right? Now this will be e prime. Because it's not moving, charges are not moving, b prime will be 0. So we kind of read, you can see x prime is that. So we can actually read from here what the answer will be. So the answer for the problem will be what happens in this frame, right? It will be moving at speed v. Okay, so we have ex, according to this, is going to be same as ex prime. So it's going to be q over 4 pi epsilon naught. X prime is going to be gamma x minus vt, and y prime is y, and z prime. So if you look at r prime vector is x prime I hat plus y prime j hat plus z prime k hat. So r prime square is just x prime square plus y prime square plus z prime square. But y prime is y and x. So this will be in the denominator. You will have x minus vt gamma square plus y square plus z square 3/2. So ex will just be like that, just from here and writing in terms of x, y, and z. How about ey? Ey is going to transform. It's going to be gamma times ey prime, because bz prime is 0. So gamma times ey prime, and ey prime is almost identical, q over 4 pi epsilon naught. Y prime is y over this denominator. Again, same thing, okay? And easy is going to be almost identical. You can see by prime is 0, so this is going to be gamma. Ez prime is going to be z prime, so it's going to be the same thing y with z. Just change y with z. How about magnetic field? Bx prime will be same as bx same as, so that will be 0. And let's look at a by. By is now this is going to be 0, but this is not going to be 0. It's going to be minus gamma u over c square Ez prime, and Ez prime is just this q over 4 pi epsilon naught, and then you have a z over this whole thing, denominator 3/2, and bz is just going to be this will give me 0 because bz prime is 0, but then it's come from y prime, so it's going to be gamma u over c square q over 4 pi epsilon naught y over this denominator 3/2. So that's so we got the electric field and magnetic field for a moving charge moving with constant speed v. So this is the answer. That's the answer for this problem. Now you might say, okay, this looks nasty, but actually you can think about it. If you try to attack it directly, how are you going to proceed? There is it's very difficult to proceed directly. But if you do it indirectly like this, you can attack it quite. At least you can attack it, and you can get the answer, the final answer. Okay, let's try to do the other problem. Okay, so it's the other problem is kind of how do I look at this in a model of this in another way. So the problem is, so we have charges along this line. Charge density is lambda coulomb per meter, and this is infinite in, and these guys are charges are moving, all of them moving with speed v. Okay, so you can think of current equals to lambda v. Okay, so we're gonna look at that, and you can see the formula will come out almost like that. All right, so we are going to do so there will be a k prime which is moving at speed v. So this is at rest with lambda, and a k which is with respect to which this is formed. So in k prime we have static electric charges of line charge density lambda coulomb lambda prime. Let's call it lambda prime. Okay, so you'll see why lambda and lambda prime are going to be different. If I watch it from here, what's the charge density, and watch it from here, what's the charge density, that they are going to be not the same. And I'll just come in a little bit. Okay, so say just going to lambda prime. So if I give you a lambda prime charge density and it's static, what is your first reactions? Electric field and magnetic field. There will be no magnetic field, so B, if I want at that point, B equal to 0. So B at point P will be 0, but electric field will not be 0. And to get the electric field, you just do a Gauss's law. So length L and distance is S, and So you make an argument, you say it has to be, electric field has to be pointed out. So, so if this is the x-axis and this is the y-axis and this is the z-axis, so suppose I'm looking at this along the z-axis, so EZ 2 pi s 2 pi s L is the surface, so this is the flux through the entire surface, and it's going to be same everywhere. So over here is E, but over here is normal, so this will be any E on this surface, so I really don't need EZ. It's just going to be E. It's going to be lambda prime L. How much charge? That's the charge enclosed. So that's the charge enclosed. So that much charge over epsilon naught. And so L cancels out. So E is equal to lambda prime over 2 pi epsilon naught s. Now, it is, if I look in this plane, YZ plane, in the YZ plane, in the YZ plane, if I'm over here, say this direction is theta, then this is the direction of electric field. If I'm over here, the electric field is in that direction. If I'm here, electric field is in that direction. Over here, I'm in that direction. So if I look at this, electric field is just pointed in the YZ plane radially out of the wire, right? So that's the direction of electric field. So if you pick a arbitrary point P in the YZ plane, then you are going to get E y is going to be E cosine theta, if I just use this diagram, and EZ equals to E sine theta. So this is the E. Now let's so we have a EY, EZ. Of course, EX is 0. So we got these are primes. These are primes. Let's call it prime in the prime frame. And I want to convert, and all the B's are 0. B primes are 0. So we want to get E's and B's by using the transformation. All right. I'm going to do that. So let's just look at get a magnetic field, because we're just trying to show that there will be magnetic field now, right? And this one you can work it out yourself. It's going to be pretty similar, but let's see magnetic field. So as for the B is concerned, in this frame, Bx will be 0 because Bx is Bx prime, and this is the direction X we're looking at. And then By will be, this will be 0 because there's nothing there because of that. And then you'll have a minus gamma u over c square, and EZ prime is going to be E sine theta. And oh, this is E prime. E prime is this. So let's write this out here. Minus gamma u over c square lambda prime over 2 pi epsilon naught s. S is the distance from the wire, okay? And might call this S prime. S prime is square root of y prime square plus z prime square. And because y prime and z prime do not change in this, so the S prime s prime is square root of y prime square plus z prime square, which is same as square root of y square plus z square, which is the same as s. So writing, and I want to write everything in this, so these are two things I'll need to decide. So this is, I decided what to look like in the K frame. I need to write K lambda prime in terms of lambda. What is lambda? Well, if I look at a unit of length and you have a lambda prime, so say this is length L prime. So in this length, how much charge there is, amount of charge is Q here is lambda prime L prime. Now if I look at from same thing, L prime, now if this is moving, this wire is moving, then from the K prime, in the K prime is L prime, but K is L, and L is actually L prime. Length shrinks, right? Moving thing will shrink, gamma. So, but and in K is lambda. So lambda times L must equal to the same thing. So lambda times L must be equal to the same amount of charge as lambda prime times L prime. And so L prime is lambda prime L gamma. And so the lambda is lambda prime gamma. So when you say lambda prime gamma, this is together is going to be lambda. So this is going to be minus u over c square lambda over 2 pi epsilon naught s. Now c square is c square equals 1 over mu naught epsilon naught. So you know this is one of the problems with carrying c. So it's going to come out there and epsilon will cancel it, right? So it's going to be minus mu naught epsilon naught lambda u over 2 pi epsilon naught s. So is cancel and you get a minus mu naught lambda u over 2 pi s. Well, if you look at with lambda and you have speed v, so if you look at any point how fast the dq dt is going on, that will be the current, right? So lambda times v will be the current. So this is I started to use u for some reason. I should use v because using v for the speed. So I'm sorry about that. V for the speed, lambda v. So lambda v. So this is current. So it's minus mu naught, and I forgot sine theta, sine theta, sine theta, sine theta, I sine theta over 2 pi s. Okay, so we got a by. Now I can go out and do bz, and you should do it out bz in the same way. So bz will turn to work out. It's going to be plus mu naught I over 2 pi s cosine theta. So as for the so putting all this together, together, we can actually summarize it here, that what we're going to see is we're going to see ex, ey, ez, this you calculate, and then you're going to get bx equal to 0, by equals to minus mu naught I over 2 pi s sine theta, and bz equals to plus mu naught I over 2 pi s cosine theta. And what is theta? In the yz plane, YZ plane, X is coming out of this, and I'm over here, and this is theta. So B is, let's call this guy some, if your magnitude, so the B magnitude, B square is BX square plus BY square plus BZ square. That will give you B equals to mu naught I over 2 pi S. This is the B that you're familiar with, and this also carries a direction, right? So direction is in minus sine theta j hat plus cosine theta k hat. If I go over there, it will be in that direction, right? Well, when sine is theta is 0, this in that direction. When theta is pi over 2, is in that direction, that direction, that direction, that direction. So you can see it has a correct. If the current is coming out, the current is coming along the x-axis, then the magnetic field will circulate like that. And it just came from, I want you to appreciate that this magnetic field is just from thinking about those drifting charges being drifting, not drifting in a frame, but drifting in another frame. And I just did frame transformation. So those drifting charges will also have electric field, right? But when we think about current in a wire, you normally have the drifting charges, electric field. You'll have electric field from non-drifting charges also, and they'll all cancel out. So this is what we have worked out is for drifting charges only. And that's why when you have a current, when you say current, you're not looking at all the charges, right? You have protons and bound electrons. So they're also creating electric fields. And if you add their electric field to this electric field, you usually get a zero electric field at this point. But you will have a magnetic field because of the electrons being drifting. Okay. The other problem, let me just guide you, and then you can just try to do that problem. So the last problem we're going to discuss was that if I have this plate with negative charges and this plate with positive charges, and so I'm looking in K frame, and these are charges, and these guys moving at speed v and v, and these are large plates, and they're separated by a distance s. Then the question is, what is the electric field and magnetic field here? Well, this is a really tough problem till you realize that I can go in a K prime frame, which is going with this speed along the x-axis, and I am actually going to have old problem of this will be minus sigma prime, and this is plus sigma, this new densities, right? And of course this from sigma prime minus sigma prime, you're just going to have electric field. And let's call this this is x direction, and this call it y direction, and we can call it z direction. So what we were gonna have is ey prime will be sigma prime over epsilon naught. Now how do I know this? Well, you can do Gauss's law. So from Gauss's law, you can for static charges in K prime frame, and Ex prime is 0 and EY prime is 0 and B prime is 0. Now when you transfer it, you're going to get a shrinking along this axis. So if you look at the, say you have a L here and L here in the in the K prime frame, L prime and L prime, okay? In the K prime, you still have L equals to L prime, but this side will shrink to L prime over gamma. And because of that, you say how much charge is in there. It's a sigma prime L prime square. You need to have same charges in, this is a K prime frame. So in K frame, you're going to have a sigma L prime square over gamma. So they will have the same amount of charges. So equating them, sigma equal to gamma sigma prime, and you use that to write everything in terms of sigma. So try to get EX, EY, EZ. So what you will see in the K frame, and BX, BY, BZ. So while magnetic field is absent there, you will see magnetic field not absent here. And the answer will be something like this. You are going to get a BZ. I think I'm going to write down BZ. BZ equals to mu naught K, where K is current density. K equals to sigma V. You are going to get this. Check. And as if this happens, if you probably have done this problem before. If you're not, maybe here is a problem. So if I have a say a current going this way, then if this current going this way, then you will have a magnetic field pointed that way. Let me see. So actually this is not correct. It's go that way, so it's in the Z direction. This is the Z direction, and same over here, current negative charge going this way, which means the current going that way. This is the negative charge moving that way, the current is going that way. And so if you do a right hand, so you will get a magnetic field from here circulating like that. So at a point between them, the two magnetic fields will actually add and gives a value like this. You can check this out, do the calculation. Doing the direct calculation using Biot-Savart law, etc., is quite hard, okay? And going around about like this makes it easier. So this is, I'm going to stop here. We can do some more problem in the future, and I'm going to talk to you another video. Okay, so if you haven't subscribed, please you can subscribe. You can like this if you enjoy this, and you can check out the website. Take care.